And next speaker is going to be Adam. Looks like we can see your screen. Sounds good. So if I'm correct, you're going to talk about other protocols for IoT, more on the wireless domain.
Yes. So
Welcome first. And,
thank you. Thanks for having
whenever
me.
you're ready.
Sure. So a little bit about myself. I'm the founder of a brand called ConnectSense. Our company Grid Connect has been in the embedded networking space for the last 20 years. Last November, we founded and launched ConnectSense, which is our line of wireless sensors for monitoring the home and office. And a little bit different than the others, we're going to talk a little bit more about hardware and communication standards.
Adam, sorry to interrupt again. I think we've lost your screen sharing. If you're using Keynote, you shouldn't go full screen, go into presentation mode. It usually messes the screen sharing. So just go through the slides and maybe not full screen.
Okay. Can you see him again?
Yes.
Okay.
Thank you.
Sorry about that. So this is a little graphic kind of outlining some of the communication standards available today. As you can see, there's a wide variety of them and just a ton of mess. So somebody that's looking to create an IoT device has a lot of decisions to make on what they're going to do, how they're going to communicate, and things like that. So the question here is, can all these wireless technologies really live in harmony? As we're all looking to move the market forward, achieve things like the smart home and all of the kind of pie in the sky goals that we have for IoT, is all this differentiation in wireless communication really holding us back from mass adoption? So kind of the questions I'd like you to keep in mind as we talk further is, should we all standardize on one wireless communication technology, and can we? Is it even possible? So primarily I'm going to talk about the four main ones that are used specifically in smart home, and I think in general across the industry right now. And those are Zigbee, Z-Wave, Bluetooth, primarily talking about BLE, and Wi-Fi. So first going to talk a little bit about Zigbee. Its physical range is around 10 to 20 meters, and it's widely known for its mesh capabilities. It's small and it's pretty low power, and it's controlled primarily by the Zigbee Alliance. So some of the things that are really advantages of Zigbee is its low power and advanced sleep capabilities. And due to the channel it operates in, it has high signal penetration ability, so the ability to go through walls. This is also because it uses 900 megahertz frequencies, so it's not a very crowded communication channel. It's very robust for getting through walls and things like that. One of the other advantages of Zigbee is that the chips are manufactured by multiple silicon vendors. So this include Texas Instruments, Atmel, Silicon Labs, Freescale, and some others. So as we'll see in some of the other standards, they're more tightly controlled. So this, having so many vendors there's a lot more chance for competition, drive the price down, things like that. You're not stuck with one vendor to do that. It also is a self-healing network. So part of that mesh architecture is the fact that if you lose one node, you're not going to lose your whole network. It's able to self-heal and reroute communication based on that node dropping. And it also allows for a large number of nodes. So in practical applications, this number is around 500, but theoretically they talk as high as 65,000 theoretical nodes. Some of the cons and things that that people don't like about Zigbee are the low data rates. So it can only do about 250 kilobits per second max. There's also some interoperability issues. So a Zigbee device from one manufacturer may or may not work with another. So that's something I've read a little bit about. And then also a gateway is generally required for internet access. So that adds some extra hardware to the mix and things you have to take into account, usually some extra cost. There's also some licensing involved where you either have to be an alliance member or do something to get approved through the alliance. Also, there's some antenna requirements that can call for a little bit larger antenna, so will cause products to be a little bit larger as well. Some of the examples where it's being used today, Philips Hue. Nest actually uses it as a secondary communication method. Here in the US, Comcast and Xfinity uses it using an iControl system, and it's also used by Crestron. Next one we're going to talk a little bit about is Z-Wave. Z-Wave is controlled by the Z-Wave Alliance. It is a physical range around 300 meters, and like Zigbee, it's also a mesh network. It, however, only has a limit of 232 nodes. Some of the things that people like about it, the low power and signal penetration, as well as the self-healing. These are all ways that it's very similar to Zigbee. But it's also been touted as being a very simple protocol that's easy to understand and design. And like Zigbee, it's also in the 900 megahertz spectrum, so it's not as crowded of a channel. Some of the cons and weaknesses that I read about, the signal, it has only one single silicon manufacturer, which is Sigma Design. So they basically control the market of Z-Wave chips, and therefore, you know, it's not as competitive of a market. Licensing, you have to go through them. So it's a little bit more controlled, closed standard. Like Zigbee, it also has a gateway required, and there's some discovery and pairing things that are required. And then also the limited number of nodes. Obviously, 232 nodes seems like a lot right now, but as we continue to add more and more IoT devices, people may find that that limit is creating some issues. Some people that use it in the market today, it's used by SmartThings, Kwikset, which is a lock manufacturer, and a product called Mi Casa Verde. Next, we're going to talk about a little bit about Bluetooth, particularly Bluetooth 4.0, which is known as Bluetooth Low Energy, or also branded as Bluetooth Smart. It typically has a range around 10 meters and a speed of around 1 megabit per second. And a lot of people talk to this about specifically around iBeacon technology. iBeacon is actually Apple's proprietary name for using Bluetooth 4.0, but it's usually often used in location and presence contexts. Some of the things people like about Bluetooth, it's high install base, creates very easy connectivity with mobile devices. And then they're working on adding some more mesh-like capabilities in Bluetooth 4.1, so then it'll have more of that same mesh network that people like about Z-Wave and Zigbee. It has a relatively simple connection and pairing process. This is something that got even simpler in Bluetooth 4.0. And then they also added the low power requirements. Some of the disadvantages, the Bluetooth 4.0 requires much newer hardware and is not as backwards compatible. And it also operates in the busy 2.4 spectrum. Where it's being used right now, primarily in smart devices and wearables, so things like the Nike Plus, smartwatches, Google Glass, and things along those lines. And lastly, I wanted to talk about Wi-Fi. Wi-Fi, the most common of these protocols used for wireless communication, likely something that all of you have in your home and workplace. So that's one of the largest advantages to Wi-Fi. It has the largest install base of any wireless communication, and it's something that most people are relatively familiar with. It has a lot of high data rates, which are obviously dependent on which version of Wi-Fi you use, and a very simple connection process that most people are very familiar with. Most of the cons and disadvantages that people talk about a lot is the power requirements. It's known as a very power-heavy protocol, and the cost of components as well. And then the busy 2.4 gigahertz spectrum, especially when you start to talk about the number of IoT devices that will be, adding in the future. That spectrum, which is already busy, is going to continue to get busier. Some examples of where it's being used in the market today: devices like the Nest thermostat and their smoke detectors, Belk and Wemo, Y-Things, Electric Imp, which is used in a number of devices, and then our ConnectSense platform also uses Wi-Fi. So I also wanted to touch a little bit on why we chose to use Wi-Fi for our particular product. We really looked at the market and the available technologies, and we wanted something that was very accessible to the wider market, especially because we wanted to touch on consumers. So we sort of started from the weaknesses of Wi-Fi and worked on ways that we could get past those problem areas, specifically around powers. So how we went about doing that was intelligently sleeping and waking the wireless when we're using battery power. So by using a secondary power processor in low power mode, we can operate on batteries for a very long time and only wake that radio on a vent or using a heartbeat, things like that. So that allows us to have a lot more flexibility and counter some of those weaknesses that are typically seen with Wi-Fi. So in summary, none of these technologies are really perfect. They each have their own strengths and weaknesses and applications where they're going to shine. In the end, the technology and the wireless communication really needs to just get out of the way of the use case and be as seamless as possible to the end consumer. And whatever technology can do this the best, I think ultimately will win out. So also, I think we all need to work together to move IoT forward. We need to be cognizant of all these things and make it as simple as possible, and just kind of continue this conversation, much like we're having today, to standardize and see where we can all work together to ensure the success and the wider market adoption of IoT. So please follow us on Twitter at ConnectSense, and we'd love to continue the conversation with you.